Okay, I don't think that įjungtas garsas. Okay. So, shall we start? Okay. Okay, welcome to this hopefully fascinating deep learning papers review today at Neurotechnology. And the topic is adding quantum to machine learning. So you might guess that that it will involve also a bit of physics, a bit of quantum computing, and finally some machine learning, of course. Okay, so let us see what we are going to be talking today. So first of all, I'm going to make a brief and hopefully, well, not so formal, quite informal introduction to quantum mechanics. Then, because this is the basis, first of all, of quantum computing, then we'll delve a little bit deeper into quantum computing itself. And finally, we'll have the prerequisites to go through some machine learning algorithms which could potentially be run on quantum computers. So let's start with the physics part, the quantum physics part. I'll talk a bit about, first of all, about different kinds of mechanics in physics, and then some basics of quantum mechanics, and finally some very very basic but also the most fundamental experiment in I guess in all of quantum mechanics, that was slit experiment, and finally we'll end this chapter with very very mystified actually in our popular culture, but in reality maybe not so phenomena, which is called quantum entanglement. So let us look what is the state of physics today. As you see here, we have classical physics, we have relativity, and we have quantum physics, and also we have, of course, the general relativity here. This part here is today is only developing. Maybe successfully, maybe not. Time will tell. Because here are all the quantum gravities, dark energies, and so on. This ellipsis here represents the four basic, let's say, basic types of mechanics which we could which we can study today. So first of all, if we are living in our usual world, as we all are, and we are traveling at bike speeds, so much less than the speed of light, and we are not very small, but we are not also very large. So we are living here in the world of classical mechanics. And then, if we somehow manage to pedal our bike to the near to the speeds of light, then we go to the realm of relativistic mechanics. If we go to very small objects like atoms, molecules, but also we are not traveling at high speeds, we are coming to the world of quantum mechanics. And finally, if we combine very small particles which travel very fast, we are arriving at so-called quantum field theory, which is like quantum mechanics on steroids. Okay, so in this review, in this talk, we will basically be concerned with the laws of quantum mechanics and what can be obtained from them. Okay, what is quantum mechanics without equations? So first of all, let's go very. I had to present these equations for the sake of completeness, but later on I will present hopefully some intuitive interpretations of these formulas here. So first of all, quantum mechanics is a mathematical theory. Uh, we, which explains some physical experiments which puzzled physicists at the beginning of 20th century and at the end of the 19th century. So, formally speaking, we have for every system we can give it a description in the so-called Hilbert space. So basically, for our we will need only to know that this Hilbert space is simply some vector space where we can do stuff like multiply vectors by some constant, take the inner product of vectors, and so on. Then a very basic thing in the quantum mechanical description is the state vector. I'll explain it later what this is and how can it be interpreted. Then, in contrast with our classical world, where we can let's say take let's say a voltmeter and measure the voltage, or take the speedometer and measure the velocity, which and all these things, they are simply numbers. In quantum mechanics, it's not like that. We have entities called observables, which correspond to these quantities that we want to measure, and they are represented in this vector space as so-called Hermitian operators, which are essentially matrices, simple matrices. Then, what's also important that that in the quantum mechanical description, these matrices, as they are Hermitian, they have their eigenvalues and eigen functions, and we can also expand actually this Hilbert space in these eigenfunctions. What does it mean? I'll explain later. Then also a fundamental thing is that nothing is certain, well, more or less, in quantum mechanics. We have essentially a probability to measure some kind of value, with which might be higher or might be lower. Of course, there are situations where this probability is 1 or 0. Then also a very important thing is that measurement is also a very strange thing in quantum mechanics. It's not like that, as I said, in our classical world, that we simply measure and the state of the system essentially remains the same. But here, after measurement, essentially the state changes, and we are left with some kind of collapsed so-called state. I'll explain it also later, how we can imagine this thing. And now the famous Schrödinger, but it should be Schrödinger equation, which governs the time evolution of this state vector, and also some other postulates which also make up the basis of quantum mechanics. Okay, so now let's see how we can imagine all these things. As I previously mentioned, if we have a classical object, in this case a car, it sits in some kind of, not some kind of, but our 3D space. So we can characterize it by its position vector and its velocity. This vector here is simply a collection of real numbers, and they are essentially definite. They don't have any spread or something like that. So it's completely exact description. Because of this, we also have in our classical world, and we all know from our intuition that objects have their trajectories. Now, in the quantum world, everything is a bit different. So as I have written here in the beginning, there was the state vector. So this state vector, you can view it as some kind of analog of this real valued vector here. The state vector is essentially simply a column vector which has not real but complex entries. And actually these complex entries here, they by themselves, they don't have any clear interpretation, but we'll see later that their modulus squared has a very important interpretation. So to sum up, the state vector essentially is the description of the system, and it contains the most information that we can have about this system. Now, what about these probabilistic outcomes I have mentioned previously? So now again, in our classical world, the car, let's say it doesn't move, so it has some definite position x0. So we can also say that the probability to find it in the position x0 is equal to 1. Now also, if we would have multiple cars at the same position, and we would measure all their positions, we would also get x0. Now in the quantum world, this is not true. For example, if we have this this our previous wave, this state vector, we can actually express it with in a suitable coordinate basis as the so-called wave function. So to imagine it, it's simply some kind of a function which, for example, has a single or multiple maxima. So now, if this wave function, let's say, describes the state of some kind of macroscopic particle, like an atom or an electron, and we have such a mountain here. This means that the highest probability when measured to find that microscopic particle is in this region here. So basically, the probability to find the atom near this x0 point is nothing other but proportional to the modulus squared of our wave function. And what's more, if we had many identical systems which were prepared in the same state, if we would measure the position of the atom or whatever, each time we would get essentially different results, because as you see here, it's only a probability, which is not one. Finally, we have come to this to the slide where the notion of measurement is a bit expanded upon. So as I said, when we have a classical object, we can measure it indefinitely, and we will always get the same result. Actually, in the quantum world, before the measurement, we had this spread out wave function. Nothing is definite. We can get many different results and so on. But now, what's very strange, and actually what our physicists till today debating the interpretation of this phenomena, is the so-called wave function collapse. So basically, it means that when we measure, let's say, the position of this atom, and we get the number x0. So this whole spread out function, it becomes a delta function. So it's just one spike in the probability this space. So now this wave function is essentially a vector with all zeros and only one entry of 1 at this position of x0. And what's more important, what's also very important, that if we subsequently measure the same atom or molecule, we will also find it in the same position. So basically, after the collapse, if we may make these measurements, the outcome doesn't change anymore. Okay, now,
Can I ask one question?
yeah.
What is measurement in quantum terms? How is it defined?
What is measurement? Essentially, a measurement is okay. So let's say we have this our isolated so-called closed system. Let's say an electron with and we want to measure its let's say position. So basically, to measure something, we have to somehow to interact with that object. So basically, if we would like to measure, okay, maybe not position, but let's say spin or something like that, which I'll talk about later. Essentially, now we have to let's say stick some kind of a probe to that in that region where that let's say particle is expected to be. Then that particle interacts with our probe, and then it collapses this wave function to some definite state, and this our probe says that yes, this particle, I found this particle in that place. Actually, a very good illustration will be in a couple of slides where I will present the two-slit experiment. So basically, to sum up, you have to when you measure something, first of all, you have to interact that system with something else from outside. Okay, so now a few words about a very strange phenomena which is not encountered in our classical world. So it's the so-called actually superposition. So what is it? So is that cat of Schrodinger's dead or alive, as this popular image say? To somehow understand what the superposition is and how it's different from the classical simply indeterminate state where we lack information about that state. Let's consider this also classical so-called Stern-Gerlach experiment, where scientists had an electron cannon. They fired electrons through a magnet, and what they saw that that these electrons, they were deflected to two definite positions actually, and also this was this discovery of the so-called spin of the electron, which we can essentially imagine as if electron were a ball, and it would spin about its axis. Well, but it's not really like that. It's simply an intrinsic property like mass or like charge. But it has the same dimension and the same physical outcomes as the angular momentum. So when we have the spin and we have a charged particle, we have a magnetic actually. Well, we have a particle which interacts with magnetic fields. So now we have it deflected to two positions. When we prepare these electrons, let's say classically, we simply sample a random number from 0 to 1, and if it's let's say smaller than some kind of number p, we have this electron in the state up. If we have otherwise, we have in a state down. So in this case, we will have simple classical probabilities here to define these particles. Now, if we have a quantum superposition here, like some kind of up and down state simultaneously. In this experiment, we will observe that we get let's say in the plus direction number of particles, which is proportional to this coefficient here, a squared, and the same as the b squared. But it seems that it's quite the same. However, now what happens if we spin this? If we turn this apparatus over at 90 degrees. Now, if we have the same classical state preparation, like simply we randomly fire electrons with spin up or down, but we simply don't know which is which. We also get these classical probabilities, and we can't distinguish which state is which. But now, if we prepare this superposition state, magic happens, and all the particles are gathered only in this spot here. Now, why is that? It's simply because when we turned this apparatus, we essentially changed the let's say the measurement basis of our particle, and in this basis, with this initial state, we have that the probability of hitting Sx plus here is 1. Okay, so now let's go to the very fundamental experiment as a QISKit experiment. We all have seen it in the schools, but it was maybe more talked about in the context of light. So, but as scientists have seen, subatomic, well, small microscopic particles are not so different. They don't have any differences with light itself, because they also can act as a wave and not as a particle. So let's see what happens here. We have a single particle source. So we fire particles. Well, let's say quite rarely. Now, if we put the one or the other barrier, and when we leave only one slit, we get these classical intensity patterns here, this one or this one. And now, if we open them both, what we don't see a simple sum of them. but we see this strange interference pattern, as if we would have shined light upon those two slits. And what's very interesting that even if we didn't have this very high frequency constant stream of particles, because maybe then somehow someone would argue that maybe one particle goes through one slit, another through another, and somehow they combine and make this interference pattern. But no, if we have, as it is written here, a single particle source, we still get this interference pattern if we leave the both slits open. So basically, it would seem that a single particle somehow manages to travel through both slits at the same time. And actually, it's something like that, because here in this picture, you see how this interference pattern is accumulated over time. So these white dots are nothing other but the places where these, let's say, electrons hit the photographic plate, and they left their mark. So at first they seem to bump in some random points. We don't see anything interesting. Now time passes. Wow, what we see? We see these stripes here, and actually these whiter regions here correspond to these maxima here. So this is also one more illustration of this probabilistic treatment of things in quantum mechanics, because even if we have some definite particle, but its position is not known. So, but over time, we have this pattern which corresponds to the probabilistic law. Okay, so now also one more thing, which is very interesting to everybody, and maybe people don't understand it correctly. We have this so-called entanglement, which Einstein in the 30s with his two friends Rosen and Podolsky, they called spooky action at a distance. So basically, the idea here, well, yeah, I like this picture from NASA very much. So we have here, let's say, two photons. Photons are particles of light, light quanta, and they also have they can be entangled. What does it mean? It means that their state, these particles are just described by a single wave vector, wave function, and they can't be separated one from another. But this entanglement actually works at a distance also. So, for example, if we somehow here created this entangled pair, let's say by some kind of physical process where two entangled photons were shot in different directions. So one travels to Alice, another travels to Bob. Now they can measure their photons which they receive. Measure that it means that, for example, they look at their polarizations, whether it's up or down, for example, something like that. And what's very interesting, that when, let's say, Alice measures her photon, then this whole big wave function, which is now spread, let's say, over the whole continent, it collapses, and we can immediately say what is the state of the another particle, another photon, which Bob has. Now it would seem that somehow here is something off, because it seems that we could in this case transmit information instantly and bypass the restriction of the light speed, but it's actually not like that. And why not? Because uh, when when Alice and Bob each receive uh, their photons, and let's say Alice measures her, Bob doesn't know what kind of state did Alice get. So to compare their findings, they still have to communicate through some kind of a classical channel, let's say by radio or something like that. So the Einstein speed of light, this restriction still applies. Okay, so that was hopefully informal introduction to the quantum mechanics. Also, instead of all these equations and stuff like that, I could simply tell you that you can go with Jesus, and quantum entanglement can be explained with Jesus. But okay, maybe somebody has uh, has this option too. Okay, now let's go to the quantum computing part. So first of all, the original idea was by Feynman. Okay, the first idea maybe in the 50s, and then more contemporary times in the early 80s. So basically, he was concerned with uh, with a question, whether it's possible to simulate some kind of a physical system, let's say a quantum system, efficiently and exactly on a classical computer. And then he proposed the idea that maybe if we want to simulate some kind of a quantum system exactly, then why don't we use a quantum system to do that simulation? So from that, scientists caught on this idea and developed it. So the main let's say superficial difference between classical computing and quantum computing is that in the classical computing we operate with bits which have two definite states, either 1 or 0. Now in the quantum computing we want to somehow utilize uh, these two previously presented phenomena of the quantum world, that is superposition and entanglement. Now, in the early 2000s, the researcher, one researcher from IBM, researcher in the quantum computing field, he published five let's say requirements that a universal quantum computer should have in order to be able to make some arbitrary calculations and implement all the fancy quantum algorithms which were already theoretically developed in the late 80s or early 90s. So first of all, here the first requirement is that it should be scalable and the qubits should be well defined. What does it mean? It means that we have to have the qubits have to be represented by some kind of a small quantum system which ideally can interact or not interact, which can be clearly separated from its surroundings. Then we also, the second requirement is that we have to have the ability to initialize qubits to some kind of a simple state. Which here it seems that it's not maybe very important issue, but okay, so in the classical computing, it's not actually very difficult to do that, but as we'll see later, initialization of qubits to some kind of a simple state or maybe even arbitrary state is one of the most difficult technological, say, tasks to implement. Then we also have to have long relevant decoherence time, longer than needed for quantum gate operations. What does it mean? It will be clearer a bit later, but for now we simply can imagine that our quantum algorithms have to run and have to end in a shorter time than the whole quantumness of the quantum processor disappears when it inevitably interacts with its environment, which can be a simple thermal motion of environment atoms. Also, the fourth requirement is that we have to have some kind of universal set of quantum gates. So it's in a complete analogy with a classical computing scenario where we simply have a few gates, and in principle we can construct them, connect them, and obtain whatever logical operation we want. So the same goes for the quantum computing as well. And also the fifth requirement, which also is not very pronounced and is not a problem in the classical computing, but in the quantum is also quite a problem. That is, we have to have the ability to measure specific qubits. And what does it mean? We have to measure these specific qubits in such a way that we don't disturb the state, very much, not very much, disturb the state of all other qubits. Okay, so why are we even looking at this quantum computing? What are its possible application areas? Well, now the prevalent thinking about these areas that they could be used in the medical and materials industries, like simply using these quantum processors to fold and to search for new medicine, or maybe search for new materials. Then we can another field is let's say supply chain logistics. That means that we might have some kind of difficult optimization problem with many variables, many outcomes, and so on. And the classical computing is computers simply can't handle so much information, and then again the quantum computers can help. In the financial services, I have read that, for example, this bank Merrill Lynch, one of the big banks on Wall Street, has already acquired, I think, this D-Wave device, and they're trying to run some risk modeling problems on it. Well, also, which is very important for us, quantum computing can be utilized in the artificial intelligence and machine learning fields. by for example, we'll see later that either by speeding up some definite steps in our classical algorithms, or even designing some completely quantum, completely new algorithms, which would not have an analog in the classical computing. Well, weather forecasting, it's also similar to maybe to the supply chain logistics field, because we have a huge amounts of data which must be stored and then efficiently processed. And finally, the cryptography here is also a very important field, because quantum effects, they can offer, let's say, not unbreakable, but very snooping proof quantum communications. So what are the specific algorithms? Some of the specific algorithms, and maybe one of the earliest ones, which were devised at first theoretically for the quantum computing. So maybe some of you have heard about the Shor's algorithms, Shor's algorithm and Grover's algorithm. So the first one is for factorization of very large, very large numbers, which actually offers, in theory, exponential speedup over classical factorization algorithms. And because of this, actually now people are talking that when the universal quantum computer is constructed and it is powerful enough, which means that it has enough qubits, then all of our cryptography, well, it can be easily um, easily broken into, because for example, all these classical methods, they are based on essentially that it is difficult to factorize big numbers. So the quantum computer can do it exponentially better. Now, also another algorithm, classical, is the search in database. This Grover's algorithm, it only, let's say, offers theoretically, I think, quadratic speedup, but still it's better than the classical ones. Then we have these basic linear algebra operations like matrix inversion, like invalid decomposition. So now I guess you can all now see that I think these algorithms will go somewhere in the machine learning algorithms of quantum computers. And also we have the quantum Fourier transform, which is also a very important algorithm in all of signal processing and so on. Okay, so now a bit of theoretical description of quantum computer and quantum computing. So what are the mathematics behind the qubits? How can we imagine them? We can imagine them very simply, actually. Let's say we have an atom which has only two energy states. So basically, the electron can be either in the lower energy state, or in the higher energy state. So this is the so-called two-level system. And now, if we have many such two-level systems, and we have means to couple them, then we get the n-qubit system, and its size is actually 2 to the power of n. This is the number of states in such a coupled system. So Now again, a single qubit simply can be thought that it is a space spanned by two vectors, the 0 vector and the 1 vector. And what's different now from the classical case is that in the classical case we would remain with these two vectors only. Simply we will have 1 0 and 0 1. But now in quantum mechanics we have the superposition thing phenomena, and we can actually have arbitrary many states which are a superposition of these two bases, so-called basis states. The only requirement here is that this vector here is normalized. So it means that the modulus, the sum of these coefficients, modulus squared, has to be equal to 1. A quite neat representation of an arbitrary vector, this representing the qubit, is the so-called Bloch sphere. So if in the classical case we would have essentially only two arrows here, like one pointing the 0 bit like straight up and the other straight down, and it would be simply a simple line, just 2 points actually. But now in the quantum case, we actually can populate with points every point on this so-called Bloch unit sphere. Now, what's also very important is to understand how the operations in the quantum computing go. For example, in the classical case, we have some electronic circuits which are comprised of let's say small switches, these transistors, which can be either on or off, and using these things we can make arbitrary logical operations. Now in the quantum world, our state which describes the qubit system is given by some state vector, and this state vector can be acted upon by a so-called unitary operator, and this operator here, it can be imagined as a matrix. So, for example, if we have a single qubit, then this operator would be 2 by 2 simple matrix. And the unitary, it means that so here the third line, it's simply that its inverse. We can its Hermitian adjoint is the same as the same matrix. Okay, so basically the computation in the quantum case goes like this. We have some kind of initial state. Let's say all the qubits are in the 0 state. Then let's say with some kind of physical process, like shining some laser pulses on these atoms which represent the qubits or the microwaves, we can a bit induce a small evolution in one or more these atoms. So this evolution would be represented by this unitary operator, and then by combining these different operations on different qubits, we can obtain our desired function. Okay, so now with an analogy with a classical computing, we have this view, the theoretical description of quantum computing using quantum gates. So these are nothing other but simple unitary operators which act on a single qubit. Thus, they are only 2 by 2 matrices. Then we also have here, for example, the swap gate acts on 2 qubits, and here we have also some gates, some operations which act on 3 qubits at the same time. So basically, for example, the identity gate doesn't do anything. It simply passes the same state. So the state that the qubit had after this gate, it remains the same. Then a very important gate is this the so-called Hadamard gate. Why is it important? Because now if we would take let's say the zero state, yes, it's like a vector 1 0, and what if we multiply this vector by this matrix here? What we get is we get a vector which is 1 over square root of 2 and 1 and 1, and this means that the Hadamard gate makes a superposition state from a simple basis state, and this to be able to perform this is a very important thing in quantum computing. Then we have some gates which are, some of them which are similar to the classical ones. For example, the NOT gate, which simply if we act with this gate on a zero state, we get the 1 state. And these are rotations actually about different axes on this Bloch sphere. And we also can have some generic phase rotation gate. We also have a swap gate which exchanges the states of 2 qubits. And for example, the controlled NOT, it also acts on 2 qubits at the same time, and it's important because with this gate we can construct entangled states. Okay, so I think in the first slide of this introduction to quantum computing, I mentioned that it is very important to have a universal set of quantum gates to be able to do some arbitrary logical operation. So there are several actually these universal sets, and for example, one of the most simple ones is comprised of these three, like the C0 gate, the Hadamard gate, and the P one quarter of P rotation. So basically, with these 3 gates, it means that combining them, we can in principle approximate any logical operation to the desired accuracy. Yeah. So how can these gates? What are the rules? How can they be combined to get something useful? So then we have these quantum gates can be combined into so-called quantum circuit. So basically, for example, here is a simple quantum teleportation circuit which does quantum teleportation. Here we see in this circuit that it has 3 lines. These lines here represent different qubits, and for example, this symbol here is a measurement gate. So maybe I'll not go very deep into explaining this circuit, but the main takeaway is that mm, when we want to describe some kind of logical or some kind of algorithm which could run on a quantum computer, we draw this quantum circuit and place these quantum gates in the necessary positions, and finally we measure the necessary qubits, and we get our desired results. One thing to remember that, as I mentioned previously, in the quantum mechanics, the measurement results are not definite; they are probabilistic. So usually for example, when we run some kind of algorithm on a quantum machine, we have to run it multiple times and then simply gather statistics on the outcomes. Okay, what are the practical difficulties of real life quantum computers? The main enemy of quantum computing, of quantum computers in the physical world, in our world, is the coherence. What does it mean? It simply means that, for example, for quantum computing to operate, uh, we have to preserve all these qubit states in this circuit. So if one point here represents some kind of let's say time delta, uh, so while this whole algorithm, the whole circuit runs, time passes. Yes, so this running time has to be smaller than this so-called decoherence time, which is simply the time in which the environment destroys all the quantum effects in our quantum processor. So it destroys the superpositions, the entanglements, and so on. So currently, for example, IBM claims that their quantum computer retains coherence for about 90 microseconds, so not that much. Uh, in this picture here is a schematic of a realistic I guess it's a superconducting qubit realization, and then here are depicted many things that can destroy our coherence in our quantum chip. So, for example, first of all, it's of course phonons. Phonons is a fancy word for a simple vibration, thermal vibration of atoms. So essentially, that's why we want to submerge our quantum chips in very low temperatures, so that this thermal movement would be as small as possible. Because as you know, in the limit of when the temperature goes to zero, to the absolute zero, it is essentially all thermal motion stops. Uh, Now another decoherence source are the photons. Uh, what it means? It simply means that our quantum chip, it's constantly bombarded by radiation of different kinds, be it I don't know, cosmic radiation, maybe electromagnetic waves of different frequencies from our environment, and so on and so on. And all these waves, they can interfere with the work of our quantum chip. So that's why these chips are also, well, scientists try to shield them as as well. Well, there are here more exotic channels, so I'll not maybe elaborate on that. Okay, so um, what do we have currently in the physical sense? What quantum computers are constructed? I have chosen here to present only two of them. I guess labs across the world, many have some kind of implementations. But for example, the D-wave quantum computer is different from all others because D-wave is an actual company which actually sells sells these machines to consumers, uh, and it would seem that it's also a very nice machine because it has 2,000 qubits. It's an enormous amount of qubits, but still people are not shouting that the universal quantum computing is here. It's because uh, this D-wave machine is quite a specific flavor of quantum computer, which is called quantum annealing computer. It basically, what it does, it simply tries to physically uh, optimize to find the least energy state of a very specific quadratic actually problem. So it's the so-called Ising glass spin glass problem. Uh, uh, so essentially it is very difficult to implement, and actually they are not even implemented. The gates that I presented previously, uh, they can't be very straightforwardly implemented on this machine, and if we want to run some kind of quantum algorithm on this machine, we have to first of all to transform our problem to that very specific form, and then only we can let the computer do the so-called adiabatic computing, and find in some time to converge to the lowest energy state, the so-called ground state, and in that ground state our result would be encoded. Now the IBM computer, uh, it's a bit different. For example, later we'll see that we can implement and actually calculate some of these quantum gates on this computer. But for now, it only has 50 qubits, and it's well. This 50 qubit version is not, I guess, it's not really tested. So for the broad population, I think they allow only to connect to the maximum 20 qubit version. So here are presented the actual schematics of the qubits themselves. So physically, in both cases, they are implemented using superconducting materials, and utilizing so-called Josephson effect in a Josephson function. So, well, basically, all this machinery here is necessary to reliably be able to construct these two states that I have mentioned previously, some kind of a ground state and some kind of one excited state, and also to these whole readouts here and couplers here, they are implemented with also with superconducting um, uh, materials. and their tuning is performed, for example, of the IBM computer with, I guess, with gigahertz range microwaves or something like that. Okay, so now that we have we had some taste of the general quantum computing, let us see what we can do from the machine learning side. So I will talk about the general ideas of the how can machine learning algorithms uh, be transformed to run on a quantum machine. So we'll review a bit how these well-known classical machine learning algorithms can be transformed. Uh, then I will also present also a hybrid classical quantum machine learning algorithm. And the last part, the most fun part, I'll present a completely quantum simple binary classifier, and then we'll see how we can implement it and run it on a physical quantum machine using the QISKit IBM API. Okay, so first of all, uh, why would we want to use quantum computing for machine learning? Well, it's just the same as I said previously, because they can perform some tasks much better, maybe exponentially faster, let's say, than classical algorithms. So, for example, there's a citation from one of the articles that I have read. So it says that if small quantum information processors can produce statistical patterns that are computationally difficult for a classical computer to produce, then perhaps they can also recognize patterns that are equally difficult to recognize classically. So, basically, we can maybe we can devise some algorithms which would tackle problems that are not, in principle, they're not tractable with a classical computer. Now, what's the difference between classical machine learning algorithm and quantum machine learning algorithm? So it seems that everything is quite the same. Only here in the quantum case, we have also two things like encoding and readout. Uh, it's in the classical computing case. Well, these two operations are pretty basic, let's say simple. Well, okay, maybe encoding is also sometimes not that easy, but in principle it can be done without great efforts. But as we will see in the quantum case, merely encoding our classical data for a quantum computer to understand it and to be able to process it is a very actually non-trivial and difficult problem. So for example, many algorithms which are devised for the quantum systems, often their creators well, don't say or forget, let's say, conveniently to say how many operations would encoding of the classical data require for their algorithm then to work on those prepared states. And The same goes a bit from a different perspective to the readout, because as I said, if we have many qubits which are all coupled, then it might be a bit difficult actually to simply to physically measure this particular, let's say, qubit or several qubits. Now, in this table here, there's a summary of some very well known machine learning algorithms, and here is the potential speed up. So we see that there are some algorithms which even offer exponential speedups. Some of them offer only quadratic ones. And now let's see in a more detail. For example, how can we implement a simple k nearest neighbor algorithm on a quantum machine, and in which stage of the classical algorithm we could use the advantages of the quantum machine. So as it turns out, we can have this speed up when calculating the distances between the different data points. For example, we can construct this simple swap test routine circuit, and essentially when we encode our quantum states with to correspond our classical data vectors like this, the distance between these two classical vectors is proportional to the overlap between these two quantum states, which are run through this swap test routine. So if we have in the classical case, let's say we have to calculate these distances using, let's say, some number of calculations which might be serial, but in the quantum case we simply input these two states prepared in a particular fashion, and then if we measure the output, we readily get this distance between the classical vectors. Then if we have quantum principal component analysis, the speedup is in the eigenvalue eigenvector calculations. The idea here is that also we have to prepare the quantum state accordingly to the classical data vector. Then we sample from those states, and we essentially can construct the so-called density matrix of the system, which corresponds to the classical covariance matrix, and then through some also quantum algorithms, we get naturally the eigenvalues and the corresponding eigenvectors. Why I say naturally? Because as maybe you remember from the very beginning, where I talked about the formulas of quantum mechanics, these measurements, they more or less they choose some kind of eigenvalue from the eigenvalue spectrum of some observable. So intuitively, quantum quantum machines should offer here an advantage in these linear algebra operations. Now, for example, the clustering can be even implemented also not only using these distance calculations, quantum distance calculations, but also on that adiabatic quantum computer, which, for example, which is in our case could be this D-wave quantum computer. So in essence, here we are mapping our clustering problem to this quadratic unconstrained binary optimization problem, and then we simply let the system to propagate adiabatically to the ground state. What does it mean adiabatically? It means that we change the Hamiltonian of the system. The Hamiltonian is an operator which essentially governs the whole time evolution of a quantum system. So we change this Hamiltonian very slowly from the initial Hamiltonian to the final Hamiltonian, and during this evolution stuff happens, and in the final state, in this ground state, our solution is encoded. So people claim that well, we can we can cast quite big problems into this optimization problem, and hopefully tackle problems which are very computationally intensive in a classical sense. Now for the quantum neural networks, for example, to construct a simple, let's say, a feed-forward, fully connected, let's say, neural network, maybe some kind of speedups could also be gained from basically from changing the classically performed linear algebra computations with the quantum ones. But also we can implement the neural networks on this adiabatic quantum computer, and for example, if we would have a lot of coupling style in this adiabatic quantum computer, that means that let's say every qubit would be connected with many others and not only the nearest neighbors. It could be shown that for example, one particular type of neural networks, the Boltzmann machine, could be even thought of as a universal quantum computing, and that means it could in principle approximate any function. Now also a very interesting article that I have found, and I don't claim to understand much in it, but people are even thinking of theories how black holes and quantum neural networks are connected. So if you'd like to read a bit about it, you can go to this preprint. But basically the idea is that somehow they construct a gravitational neural network, which then can be mapped to a quantum computer or something like that. Okay, but I thought that's a very wild idea. Okay, now for a more concrete and simple algorithm, we will see how can some classifier be implemented with so-called tensor networks on a quantum computer. First of all, what are tensor networks? Basically, they are representations, they're convenient representations which approximate a very big quantum state in some large Hilbert space. So essentially, if we have our many qubit space, we could approximate it with these tensor networks. But what's important for us is that, for example, 3 tensor networks can be expressed as quantum circuits. So, for example, here, if we have this 3 tensor network which is used in quantum many-body physics, let's say, it is equivalent to such quantum circuit where these yellow rounded rectangles represent the unitary matrices which act upon qubits. So how does this classifier work? So essentially, here we have the inputs, and here we have some quantum gates, which are unitary matrices, and with each step deeper, we have this, let's say, this dimension, the number of inputs shrinks until finally we simply have to measure our selected qubit, and its result tells us, for example, whether this is class -1 in the binary classification problem, or 1. So now, what is the training algorithm of this structure here? It resembles very much a training algorithm, actually, of a neural network. So basically, we initialize model parameters lambda, which are essentially entries of these matrices here. We initialize these values randomly. Then we set the optimizer momentum term v to 0. This optimizer which these authors used is the so-called simultaneous perturbation stochastic approximation. Basically, this is a stochastic gradient descent with momentum, which is more familiar to us. Yeah, we simply choose the then appropriate values for the constants. So basically the hyperparameters, and then we simply update. First of all, we also partition our whole training data into mini batches, and then we update these lambda parameters on each mini batch. Yeah. So, but now the loss function here is not, let's say, how in a usual, let's say, neural network or it would go. It's not some kind of a definite number, score or something like that, but it's more of it's a probability. So basically, we try to maximize this probability to classify our input vector correctly. Now, what are the results of this approach? The authors trained this network, this quantum network, with 8x8 grayscale images from MNIST. So here in this table, they represent the classification accuracies between different pairs of numbers. So as we can see that this test accuracy is is quite good. It's about on average, I guess it's something like 95%. And what are the advantages of this algorithm? Uh, First of all, the authors claim that it requires a small number of qubits, so and it can still tackle quite big real life problems. And also another good thing is that it's quite resistant to noise. Okay, now let's see another fully quantum actually binary classifier, because this one was more or less resembling what we are used to in our classical computations. But now in this case, we what we have is we have a completely quantum approach from the start. So um, first of all, our classifier is essentially some kind of distance based, and what we do is, first of all, we encode our classical data vectors into quantum state amplitudes like that, and then a very important and actually the most important step in this algorithm is the preparation of the quantum system, which can the quantum state, which can then be run through a small number of quantum gates and then measured, and then the classification label would come out. So this whole circuit looks like that. The authors used four qubits for its realization. What's very interesting here is that this whole difficult and involved part here is the preparation stage for this state here, and actually the whole, let's say, classifier is only comprised of three actually gates. So what does it how does it operate? It essentially when we have encoded our training data and also our new input vector into these four qubits during this preparation stage here. What we do then is simply apply the Hadamard gate on the first qubit. Then we measure it. Then if we get if our measurement result yields 0, then we measure the third qubit, and its result, either 0 or 1, it tells us what class does our input vector belong. Now this specific quantum circuit here is not very, let's say, universal, because the authors here manually encoded two training vectors. Like here we can see the x0 and x1 in this stage here, and they showed their results only by classifying another two vectors, x prime and x double prime. So to simulate these two vectors as well, we simply have to change this rotation gate number here. So what are the results of this, and what are the let's say the good things about it, and how can it be implemented? I tried actually to implement it on the IBM quantum chip, which IBM offers. Well, you can log in and get access to it online. So now let us see how it can be actually physically realized. Okay, so here we have this quantum experience page where we are given access to this small 5-qubit real quantum chip, and how we can operate here. We simply see again that we have these 5 lines here, which represent the 5 qubits, and we can simply drag and drop actually these quantum gates and construct this circuit which was presented here. You might notice that it has a bit more these quantum gates than it is depicted in this picture here. But that's because simply on this device and actually on many and any real devices, physical devices, quantum chips, we don't have access to the arbitrary these quantum gates. We have only a quite limited set of these quantum gates. So to simulate these more involved gates, we have to combine these simpler gates. So this is a practical illustration of this universal property of these quantum gates which are given here. So now we can simply actually either run it on a real machine, or we can simulate it. So run it on a quantum simulator. I will not click now run because it won't run actually immediately, but only after I think of a few hours, because there is a queue, I guess, because many people want to use it. So let's see what happens if we simulate it. Now we have a histogram here with two states and two values, 0.74 and 0.26. So we can see it sums up to 1. So it's so far so good, and this measurement here was actually corresponded to this measurement here. One problem with this IBM framework is that they don't give access to the controlled measurement gate, but here we have to have it, because as we read this circuit, it goes like this. We first of all measure the first qubit, then if it is 0, only then we measure the third qubit. but actually to perform this action on this machine, actually I didn't find a way, and I didn't find a way even in this Python API, which can also be used for creating these circuits, and which we'll explore in some minutes. So you could also notice that this circuit here is a bit different. It seems a bit different than the one depicted here, because the elements are a bit off. So why is that? For example, if I load this quantum circuit, voila, it seems very much like the one here. Yes, to have the mark gates, then this whole stuff here is the controlled rotation gate. Then we have also this Tifoli gate, also implemented with a lot of simpler quantum gates. So it corresponds to it. But how are those two circuits here different? The difference comes from the fact that here I created it on a custom topology. What does it mean? It means that here we have all couplings between all qubits, and these couplings are essentially going both ways. But on a real quantum chip, due to technological restrictions, we don't have all these couplings. So we have actually only such couplings, which are denoted by these red arrows. These red arrows essentially denote which qubits can be controlled by this so-called C0 gate. Because if we, for example, tried to put it on the fourth qubit, it doesn't allow us. If we put it on the qubit on the third qubit, we can only it can only be controlled by the third and the fourth, but not the first and the second. So basically, even if you have some kind of quantum computer, but you don't have enough couplings between different qubits, it might be a bit of a challenge to create some difficult and involved quantum circuits. Okay, so now the last thing to do is to see how this probability which we got here in the simulator looks in comparison with what the authors presented. So this is the so-called PACC is then the number that they got. So this one denoted by a triangle is the value which they got on the simulator, and with the asterisk is the theoretical value. And this value, which is that they got on a real quantum chip. Now, when I ran the simulation on a real chip, I think it's this one. Yeah, it's like it says that the device is the real device. I actually got a much closer value than them. So my guess is maybe that this chip maybe was a bit upgraded, calibrated better, or or maybe I just got lucky, baby, because as you remember again, these whole measurements, they are probabilistic. Okay, so basically the last thing that I wanted to show you is this QISKit API. So it's implemented in Python. So essentially we can construct and implement quantum circuits in a simple Jupyter notebook. So let's see what happens. Okay, so now these two functions here, they correspond to both these circuits which I showed you here. Okay, so let's do it. Okay, let's visualize them. 1 and 2. Yeah, as we see, we get the exact circuit as in the online quantum composer version, and also you can see here clearly that I only have this one measurement gate, because even in this QISKit framework, they still don't allow the conditional measurement, because for example, if I made this change here, so I would okay. Okay, yeah, here I get the warning that simply conditional measures currently not supported. Maybe if I would go deep into the code, maybe somehow I could implement it myself, and then I could simulate this whole circuit here. But for now, simply I didn't have well enough time to look into that. So for now, we are only stuck with this part here. Okay, so that was pretty much it that I wanted to talk about today, and may also one thing that we here talked about different equations and stuff like that, but simply you could go to this guy and learn how to become a fifth-dimensional quantum healer, and you could simply perceive all the computations intuitively, and there would be no need for a quantum computer. Okay, thank you all. Okay, so any questions?
Why you cannot just measure 2 qubits at once? So why you need conditional measurement?
Because if I measured this first qubit and then the second qubit with the second qubit also, the state would be different than that I would get if I only measured when the first qubit is 0 and not 1, because yeah.
The first qubit is 1, you just discard the second
qubit. Okay, in principle, yes, that's true, but simply to implement this in the code, it was difficult because this whole circuit is simply run in some kind of a local simulator where you first specify the whole circuit, and then you only get the essentially probabilities of these measurements. If I would somehow have access to the results of these single shots, so then I think yes, it would be possible, yes.
So what kind of quantum configures do the original authors use? Why are the
Yes,
the gates are so
actually,
different?
yes, I forgot to mention it. Actually, they also use this IBM chip, but they, I think, used another one because as you can maybe notice here, they also have this IBM Yorktown. It's maybe equivalent. It seems that, but as this paper was not from this year, but from 2017. So my guess is that simply this chip was had some kind of maybe a bit different architecture or something like that. I'm not sure, but the state today is that yeah, we can't have these conditional measurements, unfortunately.
Maybe it was calibrated as that calibration
Mm, well, this calibration, you see, it's I think it's simply when you have this physical device, uh, all these superconducting circuits there, they due to let's say environmental these couplings and so on, their parameters I imagine they drift a bit. So then this calibration is simply you have to to readjust them, but the whole architecture still remains the same. Okay. So well, yeah, you want to ask something more?
Yeah, probably because well, you implemented the binary classifier,
Yeah.
and you before mentioned the full-fledged neural networks type of architectures.
Uh, yeah, well, okay. If I had maybe access to
Require a lot of qubits or
yes, first of all, yes, and if we look at this again slide here, I think you're referring to this one, yeah. So the authors in this paper here, they claim that simply. Yes, you could in principle implement a neural net on this adiabatic quantum computer, and today I guess your best choice would be this D-wave system. But well, they simply sell them, and simple people don't have access to it. So unfortunately, it's like that. Because for example, well, I don't now remember the actual prices of one unit, but as far as I know, for example, Lockheed Martin has one, Google has one, who else? Well, all these very big, companies which want to be on the front of on the cutting edge of this whole science. So they are experimenting with it. Okay, so maybe if nobody has any questions, please go out and have some snacks.